Welcome back to Talk Universe. Today's show is for Wednesday, August 3rd, 2016. We originally had scheduled to do a show on how the virtual world was intruding on the real world. Instead, I've had a special interview with a complexity scientist by the name of Samuel Arbesman. And he's a very interesting fellow, and he has some interesting views on how some of the systems in our world, as discussed on a previous show, have become far too complex for any human to understand them, and as a result, there are some unintended actions and unintended consequences occurring. So tonight's show is all about the complexity of our real world. We're going to go back and do the virtual world interfering with the real world show very shortly. And in the following week, we are going to do a show on asteroid mining and space industry, which will be very, very interesting. So, why is our world so complicated? It turns out that the complexity of our world is growing in a way that we didn't expect. A lot of people have created systems that do specific complicated jobs, and those systems work well enough to run for years with very minor upgrades or modifications. And what happens is finally somebody retires or dies, and that software or that system is left behind, and other people often don't quite understand what it does, but they depend on it, and they build on it, and they add things to it, and pretty soon there are layers of complexity built up, and no single person understands really what's in the previous unit or how it's going to affect the new stuff. So we end up with things so complicated that nobody can fix them when they go wrong or figure out why they go wrong. Now, this is just a thing that happens when your world becomes more complicated. And the human mind is only equipped to handle so much information. We, as animals, lived in a world where the only complexity we had was nature around us and trying to understand how it worked, figuring out the calendar, growing our crops, finding safe places to live, clean water, creating shelter. And as the amount of knowledge that humanity possesses has grown over the years, and this is a common theme when I'm talking about the singularity, as that knowledge grows in complexity, the systems we build become more complicated as well. And we are sure that we understand how a thing should be done or how it should operate. And we build on it and we go with it. And before you know it, other people are saying, well, I'd like to learn about this. And they work with you. And they build systems like that. And sometimes they'll make their own little tweaks or changes. And pretty soon you've got the national power grid or the hydroelectric systems, or you've got the traffic light control systems or air traffic control. And as you can imagine, nobody really knows what's in the previous systems. And I'll give you a perfect example. Many of you have used an editor under Windows, and you find that there are certain shortcut keys built into that editor that do things like Control-C will copy whatever you've got selected, and Control-V will insert it or paste it into a document somewhere. And each of these little built-in help keys had to be created by somebody in the past. Now, unbelievably, those commands go back to the 60s and 70s when the people who first wrote the operating systems started putting all those things in. And a lot of it happened under the Unix operating system, which is an early predecessor of Linux, which many people are familiar with if they run web servers. And so, as a result, the evolution of the software from Unix to Linux to systems from Unix to DOS, your disk operating system, which had some of the same commands and structures, that evolution has created embedded assumptions that we all learn later, like a control alternate function or something like that that's in the software. And we don't know where it came from. We just know that it's in there. We assume that it's in there. And sometimes those functions don't work the way we expected. Or if we have to write an operating system from scratch for whatever reason, and they would send that escape sequence or key sequence to the old program to get it to do a job. Now somebody comes in and says, hey, I need to rewrite that system because it doesn't do this properly. And they write a different version of it. But maybe it doesn't respond the same way to those commands. Now you're in a fix. Because if you go to replace that underneath at the bottom of the pile, all the stuff built on top of it later depends on that function being exactly compatible. And unexpected failures can occur as a result because you didn't know that there was some built-in function or automatic function. That's one of the ways that our complexity is catching us up now. There isn't a magic bullet for it, and there are no, in many cases, there are no manuals to explain exactly what to look for and what you must include. In other words, there isn't a standard in many cases. Now, there are actually organizations, one is known as the IEEE, which creates standards for things like software packages and communication systems. And there's a very, very good reason for this. When you have a published standard, you can go get that standard and you can look it up and you can see what is expected when you write a certain piece of software or design a certain system. By following the standards, you know what must be there and what isn't necessary to be there. One of the recent systems that's come up in the last couple decades is the ISO 9000 series of standards for how a thing shall be manufactured, for instance. When you read that standard, and ISO stands for International Standards Organization, when you read that standard, you know exactly what's expected. You know exactly what you need to include. But even these things have variations and an evolution, a lifespan where they change over time. And so everybody always wants to know what revision or what level of standard you use. Now, this is very helpful. It's great to have those standards, but understand that many of the systems that we have today were built before such standards existed, and they stand on their own. So inadvertently, we've created a world of such complexity that it's very, very difficult for us to reckon with it. And it means that we have to go back sometimes and make upgrades or changes to a system because something breaks and there isn't a replacement for it. And we're stuck. So we're in a very precarious situation in many cases, which is one of the reasons why in many systems, older things are being phased out entirely and replaced with a new system. But again, even that isn't a guarantee that the new system will be fully compatible with what we had before. And even if it doesn't depend on the old software, it sometimes depends on assumptions that were made in the software, and we might not think that way. We might not make those assumptions when we write our code. Somebody else may use an algorithm or a method of determining when a switch is supposed to be activated based on certain inputs or certain conditions, and we might see it entirely differently. We might look at something completely different to make that decision. So as a result, we end up with a lot of trouble. So now we're going to have to look at how we can solve this. And part of it is our systems are becoming so complex, they're almost organic in nature. And we have to find a way to draw a line or compartmentalize what we're doing so that unexpected consequences don't occur. Now I'm going to introduce you to a term, and a lot of people are familiar with the term. It's called emergent behavior. Many of us are familiar with the fact that if you have a system with 2 or 3 rules in it, those rules will result in some rich or complex behavior. And when we start analyzing those rules, we might not always be able to predict what that new behavior will be when those rules are playing together. Just the same, we can put systems together with a set of rules to achieve a certain job, and generally it will work very well. A few years ago, there was a fellow who was researching the flights of birds and the schooling of fish. And he didn't know what the rules behind it were, but he found that if they stayed a certain distance apart, no more, no less, within a certain error, and if they moved together at a certain time, and if after a while some would take the lead and some would drop back, curiously, the schooling behavior or the flocking behavior or the migrating behavior would emerge. He ended up with a set of 5 rules, and when those 5 rules were put together, and they didn't seem to have anything to do with each other, but when those rules were all applied, he simulated populations of birds and fish, and they acted exactly like the real thing. What an epiphany, the understanding that this sort of behavior, which would be very complicated to program the rules for, would automatically emerge when these rules played together. So an emergent behavior is one that appears out of nowhere when a certain other set of conditions is set. Emergent behaviors have become very, very important recently because it really is a part of what happens in our natural world. In biological systems, there seems to be an incredible amount of complexity. However, once we start analyzing them, we often find that there's 2, 3, 4, 5 rules that are built into the system, and from those small number of rules, the really complicated behavior we see that would be difficult to predict or impossible to predict, and yet we expect it from those systems, those behaviors emerge apparently out of nowhere. So when we talk about emergent behavior, we talk about behaviors that were neither anticipated or perhaps programmed, and yet when we put a small number of rules together, they show up. It is inevitable that in a system as complicated as our modern world, that those sorts of emergent behaviors will show up in the most unexpected places, sometimes with dire consequences. So we know that this is one of the signs that I mentioned about the singularity. Our world is far too complex for any human mind to understand fully, or even a group of minds to understand fully. There are things that we simply aren't wired to understand because it isn't needed in nature. It's not a part of our survival. Yet, we do have the flexibility to understand abstract concepts, and we do work very well with abstraction in many levels. So, for the most part, it isn't too utterly surprising that these emergent behaviors show up. Now we just have to find a disciplinary way of fitting these things into our normal mode of thinking. In other words, we have to find a way to make our minds learn how to see and how to anticipate the emergence of these sorts of behaviors. This is something that I don't think they really teach in any schools or universities, but something that is, it's becoming something that we need to know. Because if we can't get a handle on this, we stand a very good chance of having much of the things in our world come crashing down. We'll see airplanes falling out of the sky. We'll see automobiles taking off or braking at the most unexpected times. We'll see valves opening on water systems and chemicals being dumped somewhere. We'll see power shutting down. We just don't know. Now, one of the ideas I have, and I've proposed this to a few friends, and I think it's a very good idea, we need to create what I would term a digital sandbox. We need to create a computer system that contains a simulation of an environment. And a sandbox is a place to play. You play, you work things out, you figure it out, and nothing goes outside of the sandbox and causes any damage. A digital sandbox would allow us to put our most complicated systems in there and hammer them and see how they perform. See what's wrong with them and what we need to set things right. I think that this is a really, really important idea. We need to set up a company that makes nothing but digital sandboxes and tests the complex systems in our world in the hopes that we might gain some sort of an understanding of them before it's too late. Coming up next is our interview with Dr. Samuel Arbesman, complexity scientist, and I think you'll really enjoy it. He's an interesting fellow, and he's got a lot of good things to say. Heed some of his words. Think about what he's telling us. This is Talk Universe. Okay, tonight we have a special guest. It's Samuel Arbesman. He's a scientist in residence at Lux Capital, a science and technology venture capital firm. He's also a senior fellow at the Silicon Flatiron Center of Law, Technology, and Entrepreneurship at the University of Colorado, and he's a research fellow at the Long Now Foundation. His writing on science, mathematics, and technology has appeared in the New York Times, the Wall Street Journal, and Wired. And Arbesman's first book, The Half-Life of Facts, examines how knowledge changes over time. He lives in Kansas City with his wife and children. Samuel, welcome to the show.
Thanks so much. Great to be on.
Well, we have a lot of questions, and I know people are aware that the world has seemed to become more complex over time. And man, it's a demonstrated fact now. It's so complex we can't keep up with it. And one of the items that I talked about last week was how our world has become so complicated that no single mind can understand even some of the systems in it anymore. Any thoughts about that?
I am entirely in agreement with that. And I think a lot of people realize that things are becoming more and more complex over time. And so we now have pieces of software that have millions of lines of code or tens of millions of lines of code. We have computer networks that kind of crisscross the globe. But it's one thing to say, even though these systems are very complex and maybe any layperson can't understand them, as long as there's an expert who can understand them, that's okay. I think it's another thing to recognize that there really is no expert who can understand many of these systems. And it's not as if these systems are at the periphery of our experience. More and more, these systems and technologies that we don't fully understand are on our computers, on our desks, or in our medical devices, or in our cars. And I think we are in this new era where we are now just surrounded by technological incomprehensibility.
I think that's always been a problem in times past. I think that people often would feel that if they got a degree in a specific field, they'd be able to make a real contribution and understand what's going on. Yes, it's possible to make contributions, but the issue is so many of the systems are so complex, and when we put them together, their interaction causes the emergence of new, unexpected results. And that's something we really have to deal with these days. And I know that you've made note of things such as airports shutting down and machinery going awry. What particular examples come to mind when we think about complexity overruling our intentions?
So I think one very interesting example is in the past 10 years or so, there was the case of Toyota vehicles accelerating without the drivers actually intending the cars to accelerate, which is obviously not a good thing. In this case, a number of people actually died. And there were a number of reasons initially put forth for why these cars were accelerating without control. And it turns out that none of these answers were particularly satisfactory. And eventually, through looking at the code that was inside these machines, inside the cars, it became clear that while there's no clear smoking gun, you can't point to a single line of code and say, hey, this is the reason. Essentially, it was in this case the complexity of the code, specifically the system was too complex to fully understand. It was made overly complicated. In this case, it should have actually been probably simplified and made more easily understood by the engineers and the designers. And that's pretty much the best you can do. You can kind of point to the fact that there was too much complexity in this system, and that's more likely than not the reason why these cars failed. And I think more and more we're going to see these kinds of cases where we are looking at a system and it works or it doesn't work, and we're not always entirely certain the reason why behind either the success or the failure of the system. And there's many cases where you can look at like large computer programs, and there might be a section that has comments around it saying, do not touch this. We don't know what it does. And I think this is not actually that exceptional. And there's many situations. I've written very tiny computer programs, gone back a couple of days later, and had trouble deciphering what I myself have written. And I was the one who did it. And so I think more and more we're going to see these kinds of situations where no one fully understands these things. And I think related to what you were saying about people people getting advanced degrees and becoming specialists, certainly that's one way to kind of make advances at the frontier. You get a lot of specialized knowledge, become an expert. The downside is that as more and more people are making advances, in order to make an advance at the frontier, kind of in order to contribute, you need to know more and more. And eventually there's going to be this disconnect between the amount of knowledge you actually need to know in order to become an expert and create something new, and actually the amount of stuff that you can actually learn and like actually fit into your head. And so at a certain point, specialists might not even be able to be as expert as they would like, coupled with the fact that as we build these highly interdisciplinary systems that touch upon a huge number of different domains in order to actually be functional, it's not enough to be a specialist. You actually need to have a way of understanding multiple different areas. And increasingly, as these different domains collide in these very complex technologies,
Absolutely.
Yeah, being a specialist is not enough. And I think we have to both recognize that specialists, while enormously successful and useful, they're not. And it's good that we have them, and we should continue to encourage people being specialists. it's not enough. And we're going to need people being generalists who can kind of cut across different areas, as well as just recognizing that sometimes even if you are a specialist or you are a generalist, you're never going to have a complete understanding of a system. And in many cases, that's fine. I mean, it's good to actually build these increasingly complicated and sophisticated and powerful technologies. They allow for us to do many things we would not otherwise be able to do. But the downside is that we're going to have this this mismatch between what our brains are capable of understanding and actually how these systems are built.
No, absolutely. That's a very good point. And I know that many times the most successful inventors and code writers tend to be multidisciplinarians because they understand how systems work in different applications and different situations, and they get a broader understanding of, let's say, the meta, as I guess is a good way to put it. And I know that when I write code, I try to compartmentalize each part of the task very clearly so that there isn't any leakage, no overlap from this function to the next. But there's only so far that will go when we face really complicated tasks. And, one of the things that really stands before us is nobody understands the older code, the legacy code. So explain for a moment, if you will, what legacy code or legacy systems are.
Sure. And so when you build a new technology, sometimes you try to build it whole cloth from scratch. Much more often, you build on what came before. So, for example, let's say you're trying to actually build a new computer program or a new app for your phone. Oftentimes, you're building it upon older like software packages. So rather than having to recreate knowledge and techniques for how to generate graphics, you use another package, which is a fairly standard way of building software. However, though, when you're building these systems over, let's say, long periods of time, oftentimes your technology accretes. It kind of accumulates over time. So, for example, the byproduct of this is you end up with a system like the IRS, where its technologies might some of them might have actually been invented or kind of first developed during the Kennedy administration, where the people who developed it are either long retired or perhaps even dead. But because the system is so essential for a number of different things, you end up continuing to use it and continuing to build upon it. And so you end up with these situations where the system might work, but really you don't. And there's really no one who is actively maintaining it, or really anyone on the planet who fully understands it anymore, because you end up using things that are years or decades old. And there's kind of extreme situations where, if you look at like the New York subway system, where there are these kind of like computer-like machines that are still actually running some of the subway system, and they're, I think, like well in excess of like 70 years old. I don't remember the exact number. It's like shockingly old. And you see this in case after case. And so, and in some cases, the legacy code and the legacy systems that are involved, sometimes you can't even tell anymore whether or not they're fully obsolete or whether or not they're essential for the functioning of the system. So, like, for example, and I gave the example of like a bit of computer code that says, like, with comments around it saying, like, we don't know what this does, don't touch it. And sometimes you can't even tell, like, is it essential, is it not? And you kind of prod it gently in hopes that it's not going to do anything too badly when you're modifying the system. But more and more, our technologies, because they end up growing over time, almost in this organic way, they kind of evolve over time. They end up having almost like a biological appearance, where, and the same way that we have a legacy code in our genomes, where there's bits of DNA that do things or don't do things that we no longer fully understand, or there are genes that have been co-opted over millions and millions of years, where they were initially designed for one, they kind of evolved for one function and are now being used for another function. You end up seeing the same kind of thing within our technologies.
No, that's not to be, that shouldn't be too surprising, because as it is, somebody might have spent 2 or 3 years writing, let's say, a specific application or operating system, and then when you use it, you're working on faith. You're believing that it's going to do what you think it's going to do, but that isn't always the case, as we both know. And we are in a new era of technology. That's one of the things that you're pointing out. And so a very good question is, what's the best way to think about and approach incomprehensible technologies?
So I think when people are confronted with technology that's incomprehensible, and especially stuff that not just they don't understand, but no one can understand, there's almost like two extremes that we tend towards. There's the one of fear, like fear in the face of self-driving cars that we don't fully understand, or fear in the face of the unknown. And I think that's one fairly common approach. The other extreme is this almost like reverential awe of this idea that, oh, if we can't fully understand the system, it must be this perfect like algorithmic mind. And of course, that's also not true. These systems are not perfect. They're in fact very, very messy. Even if we can't fully understand them, they're very messy. And I think in between is probably the more productive response, which is almost this humble approach to technology. This idea that we can't fully understand it, but we can still approach these technologies somewhat halfway with this kind of iterative tinkering approach, the same way that a biologist might approach a large, complicated organism, or the way a field biologist might approach a complex ecosystem.
Sort of a reductionist approach, you mean, yeah.
Well, not necessarily reductionist, but recognizing that even if you can't fully understand the entire system, you can still understand bits and pieces in order to create a more complete picture. The same way that, like, when you're confronted with an ecosystem, like an entire jungle, you might not necessarily try to understand every single organism and all their different interactions. You might say, okay, I'm going to focus on one or two different species or three different species and look at their interactions, and slowly but surely build a complete picture. And I think this kind of sense of humility towards our technology is related to that. And I actually, in my book, kind of go back to this idea that you can find in the writing of the medieval philosopher Moses Maimonides, where he was writing about that there are clear limits to what the human mind can ever understand, and he actually even gives a list of like things we'll never understand or things we'll never know, and he was fine with that. And I think over the past maybe century or so, there's been this like scientific triumphalism, this idea that if we set our minds to something, we will be able to understand everything around us, and in many cases that's true, and we've made many strides within science, and I think we should not stop. And just because we have trouble understanding something doesn't mean we should give up. But at the same time, we can actually recognize that some of these limitations also apply to our technologies, even like the things that we ourselves have built, even though we think of them as and think of ourselves as highly rational and logical, and therefore our construction should be logical as well. They're not. They're these kind of organic, messy, evolved systems that work, at least most of the time, even if we don't fully understand them. And I think recognizing that we can have a more humble approach to technology both prevents us from having this kind of fear and awe, but also leads us to continue questioning our technologies and examining them, while the other approaches often end up cutting off that sort of questioning and prodding.
Okay, and I think a lot of people don't want to admit that we've reached a point where we can't understand our own creations, and it makes them very uncomfortable. We tend to turn a blind eye to things that we can't alter or we can't understand, and that's just sort of a basic human psychological feature. Let's call it a feature instead of a flaw. But it does stand out in my mind that we've reached a point where the simple life is gone, and so many of the things that we take for granted run on the systems that nobody understands. And there's not much that can be done about that. And unless we have a new way of looking at these systems or something new to understand them, how is deep learning and artificial intelligence playing a role in all of this?
Well, I think it's playing kind of, I would say, two twin roles. So on the one hand, deep learning and AI and kind of machine learning techniques are actually helping us to better understand the systems we can't fully understand. So there have been cases where I think actually there was even one more recently in the news, but at least several years ago, Google used some of these large kind of machine learning computational approaches to better optimize how its server farms and kind of server systems were being used, right, in order to actually make their own computers more efficient. And the idea behind this is that when these systems and when these kind of computational systems are so complex, sometimes we actually need almost this machine-human partnership. We need tools, computational tools, to actually understand our own systems that we ourselves have created. So I think we're going to continue using these kinds of techniques in partnership with kind of our own, just ourselves trying to understand it. Just ourselves trying to understand these systems. So I think that's the good news. The downside is, though, oftentimes the results of deep learning and various techniques within AI and kind of neural networks, the the results might be enormously predictive, and we want to understand the underlying algorithms that generated these outputs. But oftentimes, because there's been millions of parameters being set or a huge number of variables being examined, we actually have a great deal of understanding or a great deal of trouble understanding why these algorithms gave the results they did. And so we're essentially almost like growing an answer, and the answer works, and it's very powerful. But we no longer understand why that answer works, or how that system came to that answer. And so I think we're going to end up with this kind of like, again, kind of going back to like epistemological humility, where these systems work, they can help us, and they're very powerful, but we sometimes also don't understand how the systems help us understanding our other systems. And so actually one of the perspectives I discuss in my book is there's a Yiddish term, nachas. It's kind of this like vicarious pride and joy you might have like for your children when they graduate college or they get married. And I think we might even need to start taking this sense of nachas for our own technologies, where our technologies might provide answers that are very powerful and might surprise us. And we no longer understand how they got there, but they're still our creations that we created. And so therefore we can still have a certain amount of nachas and pride, even if we no longer fully understand how they arrived at them, or we ourselves not arrived at these answers directly.
I see. And one of the things that stands out in my mind is anytime a system is well designed, when you, let's say, box up each portion of its function, you compartmentalize your design in a logical manner, you often can have a pretty good control over the end result. And so in your own domain, you can create a piece of software or a system that does pretty much what you expect. And if it ever has a piece that, let's say, doesn't do what you expect, you often can wrap around and do a little feedback to give it a control mechanism so it monitors itself. When you reach this level of complexity and then you put two or three of those together and each of them is doing its own thing and you think you're getting the right answer, sometimes something in the box is happening, like a feedback channel is building up a value or something that you didn't expect. I know that it's difficult to control complicated systems, even when it's just 2 or 3 units sometimes. We literally have millions and millions of systems tied together now, and it's amazing that they all work as well as they do. So what should we be worried about when it comes to this sort of complexity, and what should we not worry about when it comes to the technology?
So I think in terms of worrying, and I think undue worry is probably not the most productive use of everyone's time, because these systems are all around us, and if we spend all of our time worrying, we'd never do anything. I think the idea is that certainly we can recognize that these systems can go wrong, and I think recognizing that at any point something we thought we understood might fail, that can cause a certain amount of worry. What I think we shouldn't worry about is what we do with these kind of bugs and these unexpected results, because in truth, these kinds of failures they reveal the gap between kind of how we thought the system worked and how it actually does work, and so it's no longer a sense of kind of this binary understanding or not understanding a system. Now it's actually this kind of constant iterative path towards hopefully a true understanding of the system. And the idea is that while a bug does reveal the gap between how we thought it worked and how it actually does work, we can now actually make that system better, and we can now improve it. And of course, because of the nonlinear effects within these systems and the huge amount of feedback, it's still very difficult to wrap our minds around these things. But if we can find these bugs, or in truth, if we can actually inject errors into our systems in hopes of better understanding these things, I think we can gain better and more complete understandings. And in fact, going back to kind of the biological analogy, this is one of the ways that biologists understand large, complex systems. Sometimes they might actually actively mutate bacteria through chemicals or radiation in hopes of actually seeing how modified genes are actually interacting and affect the overall behavior of the organism. And people are doing the similar kind of thing within technologies. And I think we tend to worry more about technology when we view it as this very simple physics system of we know the clear relationship between the inputs and outputs. But if we recognize that these technologies are increasingly biological, that they're robust, they're resilient, but they also can be prone to failure. They're as well, then I think we might still worry about these systems, but we'll worry about them in a different way, and they will no longer seem actually quite as foreign. That if we recognize that these complex technologies, even though they touch upon every aspect of our lives, are in some ways similar to many of the living things we interact with, I think then that actually can help mitigate some of the worry and get us to think about these systems differently and create a new perspective and hopefully a more productive response towards these technologies.
No, I think you're right. I think that's actually a very good approach. I know that in times past, when the most complicated things we had to look at were the weather or living organisms, that approach worked well. You would change the conditions, see what the outcome was, and you'd put them to an extreme, and you'd see what the outcome was. So yes, it seems to me that that probably is a very logical approach to looking at our complications and to teach us about something that we can do about it, how we can understand it at the very minimum. It also would probably be a good indicator where we need to make changes or improvements just as well. So, what's the future of technological complexity in your opinion, and what's the thrust of your book, Overcomplicated?
Well, so the future of technological complexity is that it's going to be more of this, and we're not getting away from technological incomprehensibility. This is kind of a new era that we are living in, and so the computer scientist Danny Hillis has written about how we've moved from the Enlightenment, when we can kind of understand all the things around us, to the entanglement, where everything is so hopelessly interconnected that we can no longer fully understand these systems. And I think we are definitely in the entanglement, and this is going to continue occurring. And we need to have ways of at least meeting our technologies halfway. And so the thrust of my book is that we are in this new world. There are a number of forces that kind of, despite our best efforts, lead us ever more towards technological incomprehensibility. These forces like accretion over time and legacy systems and increasing interconnectivity of our technologies. And so the book kind of looks at what are the forces that lead us to this point, why our brains are not necessarily the most adapted for handling these things, and there's no good reason why our brains should be able to handle a system that has millions and millions of interacting components. We didn't really evolve to think about those kinds of things, and that's fine. But I happen to be a fairly optimistic person by disposition. I don't want to leave people, I don't want to leave my readers of my book Overcomplicated with this idea that we're in this horrible situation where we're never going to understand these technologies. And so I provide a number of different ways of at least meeting these technologies part way. And one of them is actually beginning to think more like a biologist about our technologies. And kind of use this kind of mode of biological thinking, as well as this more humble approach to our technology. And I think those kinds of approaches can make us can actually prevent us from having this kind of like fear of the unknown of these technologies that are all around us, and at least allow us to continue approaching and grappling with all the systems that increasingly we find ourselves surrounded by.
Fantastic. If you talk about this from the organic standpoint, it's pretty clear that our systems are reaching and perhaps exceeding the complexity of simple organisms like single cells and viruses and so forth. And it shouldn't be a surprise because everything seems to become more and more complicated. But don't we generally reach a plateau where there's some massive punctuated equilibrium where all of a sudden everything breaks or we find a solution right away?
So what do you mean by that?
Well, could our systems reach a point where, for instance, there are worries about our power grid going down? What happens if we reach a point where the grid goes down and nobody can figure out exactly why? Does that mean that we have to start from scratch, or that we put it back online with the certain knowledge that this could happen again?
I think in those kinds of situations, whether it's the power grid or kind of other large systems, I imagine it'll be kind of thinking about those kinds of things in parallel. On the one hand, it goes down and you end up having a whole bunch of kind of kludgy patches that work reasonably well, but there's still always a concern that we don't fully understand the system. I think that's probably the short-term solution that a lot of people will actually end up doing when our technologies go wrong. The longer-term solution of kind of rebuilding something from scratch is very laudable, and I think people do try to do that. Unfortunately, the amount of time and effort to kind of recapitulate a very complex system that has kind of evolved over time to deal with all the exceptions and edge cases of the everyday world oftentimes ends up looking more like the original system than we initially thought. And so I think it ends up being kind of this mixed process where we try to reinvent a system from scratch, it ends up probably being more modular, more cleaner, more understandable, but over time tends towards the original structure, which is more complex and maybe more incomprehensible. And so I think we're never quite getting away from this. We certainly should try and strive, and I think like rebuilding systems and kind of and thinking of new ways to simplify our surroundings is certainly a very laudable goal. Whether or not we can fully do so, I think is probably unlikely. But we certainly should not stop trying.
Okay, and the first thing that comes to mind, and I'd like to propose this as a possible solution for at least some of this. Perhaps what we should do is set up a sandbox, an AI-based sandbox, where we model some of our systems, and then we just beat the daylights out of them and find how to improve them and use the AI to converge on what we would consider an ideal or optimum solution. Wouldn't that seem to be something that perhaps with a little thought we could set up and start going through some of these older systems, truly understanding them and simplifying them?
So I think kind of having a sandbox or some sort of simulation, I think is very good actually for building new systems, but I think is also really good for actually even just trying to understand these systems. So I kind of think of the analogy of like SimCity. SimCity is obviously far more simple than a real city,
sure.
but by playing SimCity, you at least gain an understanding of the feedback and the various properties of how a system works or how a city works and kind of like the bounds of its behavior. And I think simulating a large complex technology can actually yield the same kind of insight where we could potentially use that kind of simulation to build something better. And I think that's a very important goal. But it can also be used to really figure out how to play with these systems and how to really understand the types of behavior we can expect from these systems. And I think, and because it obviously like the power grid, very complex. We're not going to just allow someone to play with it because it's very, very important and essential for a lot of life. But at the same time, if we had a simulation and people could play with it and kind of tweak its inputs or its outputs and kind of see how it responds, I think that would actually give people a lot better sense of how it might actually operate in the real world, both to potentially build a newer version, but even just to deal with the current one that we have. And so I think simulation is actually a very powerful technique for dealing with our large complex technologies.
Okay, fantastic. Well, I think this has been a great interview, and you've provided us with an awful lot of material to think about. And I want to tout your book a little bit, Overcomplicated. I think that it would be a great read for a lot of people. And is there anything that sticks in your mind as, let's say, a closing remark?
Closing remark. Well, I guess, just recognize that biological thinking and a humble approach to technology are perhaps two of the few ways forward in this new era of incomprehensibility that I think we all need to realize we are living in.
Fantastic. Well, Samuel Arbesman, I really do appreciate the time you've taken to give us this information in the interview. And we're going to put your material up on the site here, and we hope that many, many people read it and take heed. We live in a very complicated world, and we appreciate it when people such as you with your expertise can come forward and share some of the things that we should know when it comes down to complicated worlds. Thank you so much for your time.
Thank you.
Okay. Well, that was actually a very good interview with Samuel Arbesman. And he has two books that he's written that really, both of them look fascinating. The first one was The Half-Life of Facts, which he published in 2012. And basically, the subtitle is Why Everything We Know Has an Expiration Date. A lot of the things that we think we know actually turn out to have caveats or absolutely untrue later on. So that's an interesting look at how that happens and what we need to know about the changes of knowledge. The one I really would like to put forward is Overcomplicated, the one which he mentioned at the beginning of his interview. And it goes into great detail about our world and the complications in it, and much more information than he was able to present, of course, in the 30-minute interview. So I would recommend either of those, and, if you're up to it, both. For our Singularity Watch, this is a very interesting change, a very interesting turn of events. It's recently become possible, due to the higher resolution of computing that we can do and the high speed, to actually replace experimental science with computers in some cases. They have a type of software called Lab 2.0 where the computers actually do replace experimental science. Now, this is an amazing change, that we actually can use a computer to simulate enough of the real world to try an experiment and get results. So, one of the things that they pointed out, just to show the complexity of things, is to study the interactions of 3 water molecules. You have to store something around 10 to the 80th power pieces of data and do at least 10 to the 320th power mathematical operations. And that means the universe would be ending. We'd still be waiting for an answer. So that's a real bottleneck. And when we get down to the point of trying to do experimental science with a computer, it means that we have to have some serious computing capability under the hood of the machine. And that sort of capability can be done in a number of ways. Part of it is to simulate the complicated parts in a lookup table. In times past, when we had to do complex calculations very quickly, rather than actually performing the calculations, we would create a lookup table, which would have a lot of answers already pre-computed, and then we could interpolate between them and get a pretty rough estimate in a very short period of time. And that's one way of doing the task. Depending on the complexity, of course, that could be impossible. And this is sort of what's been done, however, in the case of the 3 water molecules, because really all the possible things they can do come down to electron density, a quantum mechanical probability that's pretty easy to calculate. So all you really need to know is the properties of a quantum system. And their approach, 3 fellows, Pierre Honenberg, Walter Kohn, and Liu Xiam, in 1960s, figured out how to do this. And their approach needs only 3,000 pieces of data and around 100 billion math operations. So that turns out to be something we can do very, very easily. In the 1970s, John Popel and his co-workers, other researchers, found very clever ways to simplify the computing by taking a few shortcuts, such as I mentioned, and they got it down to 300 pieces of data for 3 water molecules, and the calculations are only 100 million operations. And that can be done 500 times a second on your cell phone. So we have some pretty incredible approximation methods and some pretty powerful computing in your pocket these days. So, as it happens, we can now simulate a lot of chemical and physical systems rapidly enough and accurately enough to simulate the experiments. So this is truly an amazing step forward, and one of the things that the Singularity is holding out for us. This is one of the early yields of that sort of increase of knowledge and computing that we are living in right now. Now, I'd like to point out that a lot of people do some fairly interesting things with the most unusual computing material. And some people have actually simulated arithmetic and logic units in the game Minecraft, of all things. But if it's to the point where some game-playing hobbyists can build a working arithmetic logic unit that can be done in a game, you can imagine that with some of the higher-end chips we have available very cheaply, just a few pennies that are available right now, we can do truly astounding things. This sort of simulation is bringing us new types of solar cells and thermoelectric cells and new answers to issues like the protein folding problem, which is an extremely complex biochemical problem that has a great bearing on how compounds in our cells operate and the shapes they take. Now, that may seem like a strange thing, but consider that a protein or an enzyme works because of the shape that it is. The molecule has a specific shape when it's produced. This is an interesting thing to consider. When you're putting a molecule such as a protein together, you're literally putting it together almost like a crochet hook would in a linear fashion. But the charges, the fields on the surfaces of the amino acids that build up a protein attract and repel other parts of its molecule in such a way that the protein that's created will fold up in a very specific pattern. And the complexity of this task is so great that they once ran they once ran a competition where people were allowed to play with the job on their computer in sections and try and fold up a protein to its proper form. And now the computing power allows us to do it much, much more rapidly, and with learning systems such as Watson, the protein folding problem is being chipped away at. It's being beaten. And there are other interesting results that have come from reading such things as your genetic code and modeling the results on a computer. Today, with nothing more than a sample of tissue that weighs a few trillionths of a gram, it's possible to see within a fair degree of accuracy what somebody would look like from who that sample was taken. So you could take a cigarette butt you found on the street. You could read the proteins in the saliva's droplets that had dried on that paper, and you could identify to a pretty fair approximation what that person looked like. So we're in an amazing, amazing world right now. Another interesting story on the Singularity Watch. Ray Kurzweil, who many people are familiar with, he's made quite a name for himself over the decades in advancements in electronics, beginning with work in electronic music and moving up into artificial intelligence and transhumanism. He expresses the opinion that to merge with technology is to enhance our humanity. Now, Kurzweil is a large supporter of the singularity and what it can mean to us. And he does have some interesting and controversial views on things. Nevertheless, he does present some very interesting ideas from time to time. And many people feel that to see the most in what we can be, to enhance ourselves, to become more than what we are, is actually a true expression of our humanity. I can only say this. In the years to come, I think that the only way that humanity is going to get through this is to at least partially merge with technology. I don't know how far the limit would be and still remain human. I don't agree that to enhance yourself makes you more human. We are what we are. But I think that it has interesting possibilities, and it may be that the only way that we can live in a world of complicated thinking machines, AIs that are smarter than humans, is possibly to merge with that sort of technology. That's certainly a potential. There are many people who reject that idea, and there are many people who will fully embrace it. I'm pretty sure that Ray Kurzweil is on the embracing end of the spectrum. So ask yourself a question. If you're given the opportunity to become more capable, more than what you are, but knowing that everything comes with a cost, would you be willing to do that? And one final item for our Singularity Watch. It turns out that the poorest nations in the world are the ones that are most ably advancing the renewable energy revolution at this time. Kenya and Nicaragua in 2015 respectively met 90% and 50% of their electrical needs through renewable energies. And it turns out that Nicaragua is hoping to reach the 90% transition point by 2020 for their electrical power. Bangladesh already has 25 million people on solar energy, and India has just announced plans to power 18 million more homes with solar by 2022. And the Philippines already powers a third of its population with renewables, and they just recently announced the 7th largest solar project in the world. Now, China is now employing nearly 1 million more workers in renewables than in fossil fuels. So this is a very interesting turn of events. I know that many of us in the United States have seen that in some communities, they're actually raising your electric rates if you have solar panels. They're actually making it more difficult to get off the grid, and in some areas, they've downright condemned homes if you're off the grid. This is not acceptable. We've got to be a little more smart about what we're doing here. It looks like the countries where the supply of energy is the hardest to get and the least reliable is the one where there's the strongest push to make the most advances. Unusual that may seem, but the poorest people are working the hardest to get what they need. So we may actually see great improvements in renewable energy for the most unexpected places, third world countries, where it's the toughest to get an energy supply. And one more brief note. Artificial intelligence a lot of times works with neural networks, and they've discovered that when those networks fail, they often exhibit the same sorts of problems that people with Alzheimer's or other mental issues have. One of the signs that show that neural networks are working as we think they should is that they suffer from the same problems that organic brains have. Recently, they've discovered that while neural networks are very good at recognizing faces and spoken words, if you subtly alter an image so the neural network will think it includes something that it doesn't, it may make mistakes. So it's possible to use a neural network system for controlling access to a secured facility, and by just making minor changes to the information you're presenting to it, you may make it think that it's recognizing you properly or not recognizing you at all. So neural networks have issues that we need to confront if we're going to make them more secure. And I think that the actual answer may be to combine the actions of neural networks with strict digital processing as well. Many people are getting into the virtual reality issue in a really big way, and I do want to get back to that show. I know that many people really got into the Pokemon Go craze for a while. Its challenge was recently met. It's a played-through system now. But don't think that that's the end of it. There are many cases where virtual images are going to be overlaid on our world to provide us useful information such as maps, directions, and instructions. But one danger always shows up with that. That is advertising and misdirection. When the virtual world and the real world collide, there can be some benefits and some costs. We need to really look at the cost and some sort of a control for when the real world and the virtual world collide. Just as people have many channels that they can go to on, let's say, a music player or a radio or a television or websites you can go to on the web, just imagine how many different channels will be used to overlay our real world with virtual information, such as games, mapping information, and diagnostics and helpful information. And then just think about the intrusions that advertising can do in that sort of an environment. We're going to have to come up with something soon. We'll cover a lot of that in great detail on an upcoming show. So remember, we have everything we need to make everything we'll ever need. See, we've got a wonderful world, and every one of us is doing a little bit each day to try and make it a little better. I hope you've enjoyed the show. We're going to have another one coming up very soon where we'll talk about the virtual world. We've got a show together on asteroid mining very shortly. And we've got some special interviews coming up on that one I think you'll really enjoy. Thank you for listening to Talk Universe. This show has been for August 3rd, 2016. And enjoy yourself. Have a good life. Make the world a better place. Thank you for listening.